Thanks. Thank you. Good afternoon, everybody. Thank you for coming. I'm going to stand over here. I hope I'm not going to be in your way. Can everybody hear me okay? In the back? Well, I'm very happy to be here. This is my first time ever here, and it's a surprise to me that I haven't been here before, but it's really nice to be here today, particularly this morning when the sun was shining. It was very nice. So, as Michael mentioned, my field is primarily information theory, wireless networking, and so forth. I'm not really a power systems person, but I think many of you know that there's been a lot of interest in the last, I would say, 5 years in taking the physical layer of the electricity grid and imposing on top of that a cyber layer of sensors, actuators, communication networking, things of that sort, in order to improve the efficiency, reliability, and security of the electricity grid. Also to allow the integration of renewables, things like wind power and solar power into the grid, and to allow greater storage that comes about through things like electric vehicles, which allow storage in the home, and other types of storage technologies that are being developed. So basically, the idea is to take what a system which basically was originally conceived probably 100 years ago, that is the electricity grid, and to use some of those methods that have been used in other types of technologies to make it more efficient. And in doing this, of course, it gives the operator a lot more flexibility in how to price electricity, how to spread out the load and so forth. But it also gives the end users the ability to participate in the management of the grid. So it's going from sort of a hierarchical, centralized type of management of the grid to much more distributed grid, much more distributed management with a lot more information coming from many sensors and so forth. So because of this, there are a lot of opportunities to apply techniques that have been applied in other fields, notably, in my case, wireless networking, to the grid, so to the smart grid. So the nature of my talk today is really going to be about that. That is, looking at some ideas that have been applied successfully in wireless networking and looking at how they might be applied in electricity grids. So just as a disclaimer, I'm not a person who works in the field of power systems, so I'm going to take the attitude here that the physical layer, that is the electric system itself, can be abstracted and then look at it sort of similarly to what we do in communication systems, look at it at sort of a higher level and try to impose some systems ideas on that physical layer without worrying too much about the details. Of course, in practice, it's a very complicated physical system, and there are many things that do have to be considered. So you might think about this as being sort of a first-order look at some of these problems that before they could be applied, these ideas could be applied, would need a lot more study of the actual dynamics of the grid and so forth. So with that, let me just say what I'm going to talk about today. As the title sort of indicates, I'm going to talk about three things. First of all, I'm going to talk about game theoretic methods for modeling the interactions of entities on the grid. And then I'm going to talk about privacy in data sources and look at some applications of general ideas about privacy in data sources to some problems in smart grid. And this is mostly information theoretic here. And then I'm going to talk about this will probably be brief because it'll be at the end. I'm going to talk about some distributed algorithms for state estimation. And this is not a new area. I mean, distributed state estimation is actually a fairly old area, but there's some interesting things about the smart grid that make it, that add some interest to this problem. All right, so let me get started then, because I've got a lot to cover and I don't have that much time. So let's start out by looking at the issue of game theoretic methods for modeling interactions in the grid. And this is joint work with a number of people, but I'll mention Waleed Saad here, who's a former postdoc of mine, who's now at the University of Miami. because he's been part of most of this work. So just to motivate the idea of using game theory and to try to look at the smart grid, let me just mention a few relevant characteristics of the grid. First of all, it's a heterogeneous network. There are many different kinds of nodes, vehicles, meters, sensors, substations, loads of all sorts. And each of these nodes has its own objective. So it's like an economic system where you have a lot of different players or entities, each of which is sort of trying to maximize its own utility. There are large-scale interactions. That is a very large area, thousands if not millions of nodes, and it's dynamic and it's stochastic. Of course, things change with time because the load varies during time of day, time of year. If you have renewable sources, then those vary with the weather. And then it may even have mobility through the motion of electric cars and so forth to different parts of the grid. So these are all very similar characteristics to an economic system. And so just like in economic systems, game theory is a useful way to try to model what's going on in this situation. So, of course, game theory is not just one thing. There are many different kinds of game theory, and there are two main branches of game theory: non-cooperative game theory, or competitive games, and cooperative game theory. And I'm going to just illustrate how each of these might be applied in smart grid applications via examples. So these are not going to be very deep examples, just to give you an idea of some the kinds of problems you might use game theory for. All right, so the first example is an example of energy trading for plug-in vehicles. So plug-in vehicles mean electric cars or plug-in hybrids. So you can think about a situation where you have groups of plug-in vehicles. Say this might be a parking garage where people have driven to work in the morning, plugged their vehicle in the garage, and then as a group, that group of vehicles might think about trading energy with the main grid, because all those batteries are charged pretty much. If you didn't have to drive very far, there's excess energy there that can be sold at a profit into the grid, because in the daytime is when energy is most expensive. So you think about a situation like that where you have a number of electric vehicle groups that are distributed around, and they're all interested in trading energy in some way with the main grid. So we can model how these electric vehicle groups behave using non-cooperative game theory. Okay, and I'm just going to give you a couple of examples. First of all, if the grid acts as a single entity, so it's the power company, then this is the nature of this is as a Stackelberg or leader-follower game, where the grid is a leader setting a price, and the electric vehicle groups are followers who are going to respond to that price and competing in the market. On the other hand, if the grid elements act autonomously, then a hybrid, then we need some kind of other market model besides a leader-follower model to model the market, the price-setting mechanism. And so we can model that as a hybrid between an auction, multiplayer auction, and a Nash game, that is a zero-sum game among the electric vehicle groups. So I'm going to talk about both of these, but I'm mainly going to talk about the second one. And I'm going to talk about this when the electric vehicle groups are selling energy into the grid, and there are multiple grid elements that might be interested in buying that energy. All right, so this is the work I'm going to talk about here is in a paper that's to appear in the IEEE Transactions on Smart Grid. And so as I said, to model the market, when we have multiple buyers and multiple sellers, we can model that as a double auction. So the buyers make bids, the sellers give reserve prices. We can order the buyers in order of decreasing bids and the sellers by increasing prices. That generates a supply-demand curve. It's going to cross somewhere, and when it crosses, that sets the price in the market. And that also says determines who are going to be the buyers and who are going to be the sellers. But just the most important thing really is that this intersection point determines the price. Okay, and the price in the auction, the selling price or the trading price, is just going to be determined by the bid and reserve price, the average of the bid and reserve price at the intersection, and it's going to be a function of the supply. So the supply here is a vector, and the kth element of that vector A is the amount of energy that's being put up for sale by the kth electric vehicle group. Okay, so as this changes, then the price is going to change. Okay, as the supply changes, the price is going to change. So now, once the price is set, vehicle groups can try to maximize their utility, and we can measure utility here using the following function. So for a given vehicle group, the ith one, say, the utility of putting up an amount AI to sell into this market can be modeled as a simple linear quadratic function. The linear part is basically the profit that's going to be made by the group, and the quadratic part is a penalty that penalizes the fact that represents the fact that the energy is going to be useful at the end of the day when you get out in your car and you want to drive home. So you don't want to deplete the battery completely to make a full profit with all the energy you're going to sell, because you need to have something left to drive home at night. So, you know, this is a quadratic penalty, but it could be other things, but this is a typical utility function in the literature. So how can we solve this game and find a Nash equilibrium? Well, because of the auction, this is a very difficult analytical problem. So, for example, what happens here, as the vehicle groups play the game in sequence or choose their strategies in sequence, the supply-demand curve shifts, and so the price changes. So it's a very complicated dynamic going on here. It's very hard to solve in closed form, but it's very simple to look at this game algorithmically. That is, you can simulate it very easily and using best response. Best response just meaning that in turn, each of the vehicle groups maximizes utility, the price shifts, the next vehicle group maximizes its utility, and so forth, and you keep doing that until convergence. So here's just a typical simulation. This shows the average utility. The utility is that linear quadratic function I showed you, per electric vehicle group versus the number of groups for two different strategies. One is this Nash game, which you can see gives you a high utility for low numbers of electric vehicle groups. The utility falls off, though, as the number of vehicle groups goes up because there's an increased supply, which, of course, the laws of economics, that means that the price comes down. On the other hand, there's still a significant increase in average utility per group over the so-called greedy algorithm, which is just a situation where each electric vehicle group sells its maximum possible into the main grid, so without consideration of playing this game. So you can see that modeling this as a game with this utility gives us insight into what would happen in the marketplace and how that would improve the position of the electric vehicle groups over a simple situation where they sell energy directly into the market without consideration of the fact that there are other electric vehicle groups there. We can also look at this Stackelberg case where there's a single entity in the grid, so we don't have to run an auction, because then the single entity in the grid could act as a leader, setting a price, and the other members of the electric vehicle groups then act as followers. They play basically a Nash game to determine how much to trade. And there's another paper here. This is, again, Walid. This is Ways Tushar, another former visitor in my group who's at the Australian National University. And this appeared in the Transactions on Smart Grid last year, I think it's September. And here, this is actually, we're looking at where the vehicle groups are buying, not selling. But it's very similar. Basically, it's a dual kind of problem. The vehicle groups still have linear quadratic utilities. The price is set by the leader, not by auction. And the leader's utility is bilinear, that is, it's just price times total quantity sold. This game is tame enough that we can actually analytically find a Stackelberg equilibrium in closed form. So it's a much nicer game than the one that I just showed you where we have the auction in the loop. And we get a closed form solution, and we can look at various, these actually say simulation results, but these are actually computational results. We can look at the price at Stackelberg equilibrium versus the number of groups. And the different curves here correspond to different total amounts of supply in the grid. So there's more supply for the smaller, it's hard to see these numbers, but there's more supply for the lower curve than there is for the higher curve. So there's just the law of supply and demand. Here, since the vehicle groups are buying, not selling, the price is going up as the number of vehicle groups goes up. And this is just the average utility versus the number of groups, and we see similar behavior to what we saw in the other case. Okay. Don't worry about these other curves here. These are two other algorithms that do something else, but you can see that the sort of Stackelberg game is better than those, but I don't have time really to talk about what those are doing. So now let me go to an example of an application of game theory where we would want to use cooperative games. And this is the problem of a microgrid interaction. So in the electricity grid, you have a high voltage part, a transmission grid, a transmission network, and then the voltages step down into lower voltages that are used actually in the so-called distribution network. So you have, or the distribution grid. So there's where we are. That's where loads are, small loads, houses, and things like that. It's where renewables live. So if you have a solar array on your roof, it would be a microgrid element. And typically all these microgrid elements would trade energy with the main grid. So like a solar array would sell energy into the grid, and a load would buy energy from the main grid. Okay. So, but if these microgrid elements were to cooperate, they could exchange energy with one another. That is, they could sell surplus and buy. Those that have surplus could sell surplus. Those that need energy, that is, are in deficit, could buy energy from other microgrid elements. And in doing that, they might save something over simply trading with the main transmission grid. So one thing we might look at, for example, is trying to reduce power losses over transmission lines by trading within the distribution network. You could also do pricing and other things like that, but just in this example, I'm going to look at power losses. So this is a good situation for which you can apply so-called coalitional games. So I'll say what those are. So a coalitional game is, again, you have a set of players, N players, and those players can form coalitions. So a coalition is just a group of cooperating players. And a coalition, there's a set function, V, a value function, which is like a utility, which is assigned to a coalition. So when you form a coalition, that coalition has some value associated with it. And then that value can be apportioned out to the players in the coalition. So there's a payoff function, which pays the ith player phi I of S, in the ith player in coalition S, an amount phi I of S for being in the coalition. Okay, and so for illustration purposes, we'll use power losses, and I'm not going to put any formulas up for this, but there are in the literature, there are models that we can use and have used. But once we have sort of a model for the power losses, we can turn that into a value of a coalition, and which has to do with the amount you save by forming the coalition compared to trading directly with the main grid. That can be apportioned out to the players according to how much they contribute to that value. And that gives us then these payoff sets of payoff functions that can be compared based on so-called Pareto ordering. That is, you can compare two coalitions one coalition compared to a second coalition, the second coalition is better in terms of the Pareto ordering if at least one member of the new coalition is better off than before and no member is worse off. Okay, so that's Pareto ordering is like social ordering of the coalitions. So once we have an ordering, if we define value, payoffs, and an ordering, then we can start iterating on coalitions using merging and splitting. So we can start out with some basic coalitions, start merging coalitions, splitting off players, and so forth until we get to some limit. And you always will converge to a stable merge and split proof limit when you do this kind of process. So again, I don't have any analytical results here, but I'll just show an example. This is an example where you have 10 microgrid elements of various sorts. Some are buyers, some are sellers, in a 10 kilometer by 10 kilometer region. The macro station's in the middle. And this just shows a single realization of a simulation. So this is just a snapshot. But it shows you that coalitions are formed, a non-trivial coalition. So you don't form the grand coalition where everybody's in a coalition. But you also, likewise, you don't also have everybody trading with a macro grid. So there's something in between that's better than either one of those. And that comes about by doing this coalition formation. So this is just one snapshot, but if we do run that over a large number of such snapshots, we can get some average results, and this shows the average cost, which is power loss per microgrid, microgrid element versus the number of microgrids. And the red curve here shows the average cost per microgrid for the coalition formation game that I just mentioned. And the blue curve shows what's called the classical non-cooperative scheme, which is when all the microgrid elements just trade directly with the macro grid. Okay, so you can see that coalition formation is very favorable, particularly when you have a lot of microgrids, as you might expect. Well, let me just wrap this up because I want to have plenty of time to talk about the other two things. So basically, just with a couple of examples, I've illustrated how game theory can be used for smart grid modeling. Two things I talked about here. One is demand side management, meaning having the loads participate in the management of the grid, so in this case through energy trading. I also talked briefly about this problem of integrating microgrids into the distribution network. And I'll just point out a paper here. This appeared in the Signal Processing magazine in September, which talks about these two problems and a lot of other problems where game theory can be applied in a smart grid. This was a special issue on smart grid of the Signal Processing magazine. Now, a couple of other problems of interest. This one is a little bit more in line with a communication problem where one of the things that the smart grid involves is a lot of data being collected by sensors and meters and so forth that has to be backhauled through the network to some collection point. Okay, so one way to do that is to use the power lines themselves for the backhaul. And a characteristic of power line communications is that it has very wide bandwidth over short distances, but the bandwidth falls off very rapidly on long distances. So you have to use multi-hop communications to do that, which means that all the data sources are competing for the same resources to backhaul their data. So you can set that up as a network formation game, which is in this case a Nash game with payoff being delay. So utility is basically the negative of delay. And that allows you to set up, that gives you a way to set up a protocol for backhauling data in this kind of competitive market. We can also look at other things. I mentioned social optimality in the setting of coalition formation, but you can also try to impose that on trading markets as well. We had a paper at ICC in Budapest, again this is Ways, which talks about that problem as well. Just a couple of other things, just like in communication networks, we're often interested in cross-layer optimization. And it's the same thing here, right? We have the physical layer, which is the electricity grid itself, the power system. We have the cyber layer, which is mainly what I've been talking about here. There's also an economic layer on top of that. And even on that, at least in the US, there's a political layer because utilities are regulated by government. So there's a lot of interesting interplay here, just like you have in a communication network. There's a lot of layers to think about, and they all behave differently and have different dynamics and so forth. Also, I didn't talk at all about dynamics really. I mentioned it at the beginning, but everything in the electricity grid is changing with time. So really you need to look at game theory in a productive way. You really need to look at dynamic games, and I think there's a lot of interesting stuff that can be done there. All right, well let me shift gears now and talk about the second problem I want to talk about, which is basically privacy in data sources. And I'm going to talk about applications in smart grid, but I'm going to start out by talking about a fairly generic problem, and then you'll see how it applies to smart grid. And this is joint work with several people, one of whom is Denise, who's sitting there. But a lot of the work I'm going to talk about most was with Lalitha Shankar, who's another former postdoc of mine who now is at Arizona State. All right, so here's the basic motivation here. We know that there's a lot of electronic information about us out there, okay? A lot of it comes from social media or other interactions with the web, but also the electricity grid generates information about us too through smart metering and other types of sensing. Now the reason, of course, this data exists is because it's useful, and the utility of that data of these sources of information depends on their accessibility to people who want to use it. On the other hand, this is very, today we talk about this a lot, accessibility of electronic information sources also can leak private information that's not supposed to get out there, okay? So there's a basic fundamental trade-off here in in the utility or the use of electronic storage, electronic information sources, between utility of the source through accessibility and leakage of privacy. Okay, so first question I'm going to address is how can we characterize this fundamental trade-off? All right, well, to look at that problem in a sort of more abstract setting, let's look at a database. I'll come back to the grid in a minute, but let's look at a database problem. So a database is basically a table, and it has, say, n entries, where an entry is a person or an event whose data is captured in the database. And the columns are attributes. They correspond to attributes of the entry. So for example, in a medical database, an entry might be a patient or a visit of a patient, and the attributes would be things like demographic things like age, gender, so forth, the date of the visit, test run, diagnosis, treatment, response, and so forth. Okay. And then the way, of course, the database is used is a user queries the database, and the database sends back a response based on that query. All right, so we can model that mathematically as a sequence of n, so the rows there are n of them, and they're corresponding to different entities whose data is stored there. So we could think of the rows just as first order as being independent and identically distributed random vectors and drawn from some distribution, say p sub x. Okay, so the rows we can model them roughly as being independent. The columns, of course, are going to be highly correlated. So for example, in a medical database, the age and gender might be highly correlated with the tests that are run for given symptoms and so forth. So we can divide these attributes typically into two types: public ones, that is ones that we'd like to reveal, and private ones, that is ones that we'd like to keep hidden. And these may not be disjoint. That is, there could be some variables that are both hidden and revealed. So for example, you might in a financial database, your credit card number might be there, and of course that would be hidden. but the last 4 digits might be revealed in order to, so that you can identify which credit card someone's talking about when they say they've charged something. But even if they're not, even if they are disjoint, the fact that they might be correlated gives rise to the possibility that there's going to be information leakage, right? So even without overlap, the fact that this is not a product distribution means that in revealing the reveal database, the public variables, there's going to be potential for leakage about the private variables. Excuse me. Okay, so let me just contrast this problem to the problem of secrecy. I know some of you are taking a course on information theoretic secrecy or physical layer secrecy. And of course, there's been a lot of interest lately in using information theory to try to characterize and understand secrecy at the physical layer of wireless communication networks. Okay, and in that kind of problem, basically you have a source of information that's going to be sent to a legitimate receiver who should receive that source. And then out there are also eavesdropping receivers, maybe an eavesdropper. So there are two types of, there's one type of information, there's a single source, and two types of receivers, legitimate and basically illegitimate or eavesdropping. Now in the privacy problem, we have a different problem. Really, there's only one receiver. That's the query initiator, the querier, who is a legitimate receiver, a legitimate user of the database, okay, or a legitimate receiver of information. But the source itself is dichotomous. So here it's the source, there's a single source and a dichotomous reception. Here there's single receiver but dichotomous source. That is, even though the querier is legitimate user of the database, some of the data should not be revealed to the querier. Okay, so the dichotomy is pushed to the other end of the transaction compared to the secrecy problem. Okay, so that's just an aside. So now we have this model, we have NIID random vectors from a joint distribution. How can we characterize the trade-off between utility and privacy in this setting when we have these public and private variables? All right, well, a natural way to measure utility is in terms of distortion. So distortion is sort of an inverse measure of utility. And here we want to talk about distortion of the public variables as revealed to a user of the database. So low distortion means high utility. And we're only worried about distortion of the public variables. Now, to measure privacy, we're really interested in these private variables. And we can measure privacy taking a page from the playbook of the physical layer secrecy community. We can measure privacy in terms of the equivocation of the private variables in information revealed to a user. So equivocation is just a word for conditional entropy. And so the higher the entropy of the private variables given the information revealed to a user, the better off we are in terms of privacy. Okay, so we want equivocation to be large and we want distortion to be small, okay, albeit with the different sets of variables. So that gives rise to a distortion equivocation region that we can think about as describing the trade-off between utility and privacy in a data source. Okay, so now this is really a mathematical problem. We have these are mathematically defined things. Once we set up a metric, we can define distortion. We have IID sequence of vectors. So now we just have to go to town and try to analyze this problem. Okay, well to do that, we can map it into a communications problem. At least for me, it's good to map it into a communications problem. And this is, what I'm going to talk about here is joint work with Lalitha, whom I mentioned before, and Raj Rajagopalan. And this appeared in the Transactions on Information Forensics and Security earlier this year. I think it might have been March. So we can think about revealing a database to a user or to a querier as a type of encoding. So we take the database, which is just a sequence of random vectors, and quantize it, okay, that is encode it, into one of a finite number of possible databases. And these are called sanitized databases, and that term comes from computer science literature on database privacy. So that then lets us think of this like a communication problem. We have a source, which is the database, or it could be another information source. It consists of two types of variables, revealed and hidden. That source is encoded by quantizing it into one of a finite number of possible values. That's revealed to the user or the querier, which is, we call it decoder here, who then tries to reconstruct the revealed variables from whatever is revealed from the encoder. Okay. Now we measure utility of that reconstruction in terms of distortion. So if we set up a distortion metric to measure the distortion on those revealed variables, then what we'd like to do is for that to be no larger than some amount d, and here in expectation, and here we'll, because this is information theory, we'll add a little epsilon, which is going to go to 0 as the size of the database n goes to infinity. Now we're going to measure privacy. So this is a measure of utility. Privacy we're going to measure in terms of equivocation on the hidden variables given what's revealed to the decoder. Okay? So again, equivocation is just conditional entropy. This is per line or per row. And we'd like that to be greater than some amount capital E. And again, we'll offset that with a little epsilon that's going to go to 0 as n goes to infinity. Okay. So now what we'd like to do is define for a given, as n goes to infinity, for a given joint distribution, a given row, and given, that's all we need to know, given partition of revealed and hidden, we'd like to find the achievable set of D's and E's. Okay, that's the region we're looking for. Now this problem is made easier by adding yet another variable, and that's rate. So in particular, if we add a rate constraint on the encoder, meaning an upper bound on how large m can be, so that introduces a rate parameter, which is, you can think of as being bits per entry revealed per query. Okay. Then we have a triple, rate, distortion, equivocation, which looks like a harder problem, but in fact it's an easier problem to solve because it becomes a classical problem in information theory. Forget about equivocation now. The rate distortion trade-off is one of the classical problems of information theory. So for a given source, there's a lot known about how to compute the rate distortion function. Okay. Now rate distortion with an equivocation constraint is also a known problem, studied in a much simpler setting by Yamamoto 30 years ago. So there is machinery out there for approaching that problem. It has to be updated for this more complicated problem, but there is machinery that can be used. So in particular, we can often find the rate distortion equivocation region, which is going to look something like this. We have three axes, equivocation, distortion, and rate. And for a given achievable distortion equivocation pair, there's going to be a minimum rate that allows us to achieve that. So that gives us a surface. And every rate above that is achievable. Okay. So if you look at the projection of that surface onto the distortion rate plane, you get the classical rate distortion function. Okay. And if you look at the projection down onto the distortion equivocation plane, that's really what we want. We're not interested in rate distortion. We're not really interested in rate at all. We just want to, it allows us as an intermediate step to get what we want. So if we look at that projection down there, we're going to get basically the privacy utility region, and the outer boundary is going to be the efficient frontier of that. That is, any point we pick here for a given level of privacy, this is going to tell us how much utility we have to sacrifice or how much utility we can achieve, and vice versa. Okay, so that's a general formalism, and now I want to talk about applying that in some smart grid problems. I'll do that very briefly. Okay, the first problem I want to talk about is a problem called competitive privacy. So it's a variation on the problem I just told you about. Okay, so this is the way the electricity grid is organized in North America. There's these so-called regional transmission organizations that jointly manage the grids. They're independent of one another, but they jointly manage the grid. So I live in New Jersey, so there's one called PJM, which is Pennsylvania, Jersey, and Maryland, that manages the grid, manages my electricity grid. And so these are, entities that have to work together because on the boundaries, of course, electricity flows, but they're competing entities. Okay, so they need to share, in order to reliably manage the grid, they have to share measurements, okay, to estimate the state of the grid. So that's the utility of information sharing here. On the other hand, they're competitors, so they'd like to withhold as much information as they can from their competitors. So there's a utility privacy trade-off here for any of these RTOs, and since they're all interacting together, this is actually a problem in competitive privacy. That is, they're competing with one another, they all are trying to trade off utility and privacy, at the same time they're all interacting with one another. So this is sort of a generalization of the problem I just mentioned. Okay. So how can we model that? This is a paper that was presented at Asilomar last November. This is Lalitha again, and this is Shomo Kar, who's another former postdoc of mine now at Carnegie Mellon. So for the kth RTO, we can model this situation as the following. Let's assume there's a system state associated with each RTO. So it could be some voltage phase angles or something like that. And the grids are all interconnected, so what the measurements that RTO-K makes is a linear combination of all the states of all the RTOs and plus noise. So this looks like a multiple access channel, basically. So again, we can see a communications problem coming up here. The utility for RTO-K we can measure in terms of distortion. So we can measure it in terms of mean squared error in estimating its own state. And privacy for RTO-K we can measure by leakage of information about its own state to other RTOs. Okay, so this is not exactly equivocation that we're going to use in this problem, but it's something like that. Okay. Now it turns out that this problem can be solved in a very natural way, and when you see the solution, if you're familiar with this problem, you'll see why. In fact, for the two RTO case, you can show that the optimal trade-off between privacy and utility in this problem comes about by using Wiener-Ziv coding to share information. So Wiener-Ziv coding is optimal distributed source coding for correlated sources. Okay, so that's what Wiener-Ziv coding refers to. And it's optimal in the sense of minimizing the rate of transmission. Okay, so you can see that basically we have a Wiener-Ziv problem here. We're trying to reconstruct a variable. Okay, that's source coding is used to do that. But we're trying to minimize rate, and here rate is leakage of information. So you can almost see automatically once you formulated this problem in this way that the answer is going to be Wiener-Ziv coding. All right, well let me talk about another problem. This is a smart meter privacy problem. So a smart meter is just a meter that transmits data about what's happening in the premises, electricity usage, in almost a real-time basis. Okay, do you have smart meters in Sweden? Is that a thing here? So this is used. This is in the U.S. I think I know in China. Pardon? In the EU. It's requirement that 5,000. Okay, so this is coming. Okay, if it's not already here, it's coming. In some places in the U.S., like California, it's like Northern California, it's already there, and it's coming. So if you look at the this is a cartoon, but it sort of shows what it really looks like. The trace of a meter throughout the day looks something like this. So you see you have a lot of background stuff like the refrigerator, air conditioner, and so forth. You have a lot of transient events when people turn on the tea kettle, a microwave oven, television set, and so forth. Now, smart metadata is useful because it allows you to do load balancing, pricing, and so forth to try to make the system more efficient. That's why it's a requirement in the EU and other places. On the other hand, it's pretty clear that if you have this data, you can see what's happening inside the house. Okay, so particularly you can see when somebody's at home, you can guess when they're not home, and so forth. So you can see there's again a privacy utility trade-off in this problem. Okay. Now I'll just skip the details, but if we model this in a certain way, this is now a time series problem. It's not an IID sequence anymore, but we can get around that by modeling it as a Gauss-Markov problem. And it turns out that we get an optimal trade-off between privacy and utility here by doing so-called reverse water filling in the power spectrum. That is, if we look at the power spectrum of what's coming off the meter, the measurements, then what we want to do is to set a water level, I guess it's called phi here, and suppress those elements that have energy or power spectral density less than that amount. Okay, and now so the motivation for this, or the intuition behind this, is that the low power events here are these short-lived ones. Okay, even though they have instantaneous, have high power, in the long term, most of the power is being drawn by these sort of more steady things like air conditioners and refrigerators and so forth. So that's really the big money in terms of saving power. These transients, though, are the most revealing. So by suppressing the transients and letting the other things go through, we're sort of doing the optimal thing in terms of trading off utility and privacy. And of course, the efficient frontier, you can move around it by moving the water level up and down. Okay, higher water level means greater privacy, less utility. Lower water level is the opposite. Now, you can also make this problem more sophisticated by adding energy storage. So if you have a battery in your house, say an electric vehicle in the garage, or if you add energy sources like renewables, you can actually then introduce a control problem which allows you to use those resources instead of, say, signal processing at the meter to suppress things. You can actually use, say, energy storage to be sure that you're just not drawing power for those events. You just draw it off the battery and so forth. And this is in joint work with Onur Tan and Denise Kunduz, which appeared in the Smart Grid JSAC series earlier this year. Okay, so just let me wrap this part up, and I'll be quick on the last part, so I'll be sure and finish on time. So basically, we set up this problem where we have an information source. We want to divide it into public and private parts. This leads to this equivocation, distortion, characterization. We added rate as a third variable, which allowed us to then think of this as a more traditional information theoretic problem that we can then get at solutions for. I talked about these two applications to the smart grid, competitive privacy and smart metering. And I'll just point out that there's a lot of other things you can look at in this general formalism. For example, you know, the formalism I showed you is a single query formalism, but you could, of course, continue to ask the database over and over for information, and that might change things, and in fact it does. And you can analyze that as a problem of successive disclosure. Also, you might have multiple sources, that is, multiple databases, and so you can think about that as being the same problem, distortion, equivocation, trade-off problem with side information. So you have another database as side information for that problem. So then these again bring up other information theoretic machinery that you can use to attack these problems. Okay, well, I'm going to go quickly over the last one of these, and this is a problem of using distributed algorithms for state estimation. And this work I'm going to talk about here is joint work with Le Xi, who's not a former postdoc of mine. He's a professor at Texas A&M University, and Le is actually a power systems guy, so he's a useful collaborator in this work. So let me just motivate this very briefly. So here the idea, the motivation is the following. So, you know, as I mentioned earlier, one of the features of the smart grid is more sensing. Okay, so if you have fast sensing, so-called phaser measurement units, which take measurements much more rapidly than more traditional SCADA systems do, this produces big data. If you've got all these meters and sensors out there producing data, you've got the possibility of communication bottlenecks. I mean, if you have a very large grid, say all over North America, it's impossible to think about backhauling all that data to some central point and doing, say, state estimation. Okay. At the same time, there's a lot more independent RTOs, which here I'm going to call control areas, that is areas where state estimates are being used to control the grid or local parts of the grid. It's important that they all have situational awareness. That is, they need to know what's going on so that they can effectively manage what's going on. So for these reasons, it's of interest to look at the problem of distributed estimation so that these control areas can build some idea about the system-wide state based only on their own measurements and information exchange with their neighbors. Okay. Now, I mentioned earlier that, distributed state estimation is not a new problem. It goes back at least to the 70s. Alan Wilsky did a lot of work in this area back in the 70s. But an interesting thing about the problem about this particular application is that the thing we're estimating, there's basically two networks. The thing we're estimating the state of is the electricity grid, which has one sort of topology. And the communications information or the sharing of data is handled by another network, namely the cyber network, which has another topology. Okay, so they're not the same topologies necessarily. So they're two different topologies, and they're going to interact in some way to determine the properties of state estimation. So even though this is an old problem, this is sort of a new twist on the problem where information sharing is happening over a different network than the system that we're trying to estimate the state of. So we can model this, at least for a DC model, in this way. So the system state we're interested in here is just the vector consisting of all voltage phase angles of all buses in all control areas, so the whole grid, okay, the state of the whole grid. And each local control area, say the nth one, has a model, has a measurement like this of that state. It's just a linear, in a DC model, it's a linear measurement of the state plus noise, where the matrix H is the Jacobian representing the local physical connections of the grid around control area N. Okay, so given these measurements, what we'd like to do is to somehow create estimates of theta based on only these measurements and measurements that can be gotten from the neighborhood, in the cyber neighborhood of the nth control area. And here's an algorithm that does this. This appeared also in the Transactions on Smart Grid last year. So this is an iterative algorithm for the nth control area to estimate the entire state. So xn of t is the state, is the nth control area's estimate of theta at time t. We iterate in this way. At time t plus 1, we look at the old state estimate, and we correct it in two ways. That is, we update it based on, say, a traditional type of update, which is just incorporation of the residual error, and that goes through the Jacobian of the physical connectivity of the grid. And then we have another term, which is a consensus correction. That is, omega n is the communication neighborhood of the control area, the cyber neighborhood. And these are the state estimates of all its neighbors. And what we'd like to do is to drive the consensus to drive this term to 0, just like we'd like to drive this term to 0, by achieving consensus in our neighborhood about what the state is. Okay, so this is, and then there are these coefficients, beta and alpha, which are just tuning constants of the algorithm. So it turns out that if the grid is globally observable, that is, if the sum of all these Jacobians transposed times themselves is a full rank, that means that we could estimate the state if we saw all the measurements. And the communication network is connected, not fully connected, but just connected, meaning you can get from any point to any other point through multi-hop communications. And there's a mathematical test for that. And then these two conditions assure that all the local estimates converge almost surely to the global least squares, okay, if we appropriately program the alphas and betas. So this is, as with any adaptive algorithms, the tuning constants need to be, they need to sum to, they need to have they need to go to 0, but not too fast, okay. So here we get local almost sure convergence to the global estimate. And just to show a couple of examples, these are two standard test bus systems, IEEE 14 bus, IEEE 118 bus systems. These are globally observable systems. All of the control areas which are shown in these blocks are globally unobservable. That is, none of the control areas can estimate the entire state on its own. The shaded ones are actually locally unobservable, meaning these control areas can't even estimate their own state on their own. Okay. There are two communication networks shown. There's a red one and a black one. In each case, these are connected. So this satisfies the conditions: a globally observable system, a globally observable physical system, connected cyber system. And if we look at the algorithm, we know it has to converge, but we can just show ourselves that by running it. This just shows convergence to global least squares of a few of the phase angle states in each of these two systems, and you can see that as it has to do, they do converge. Also, we can see a bit of robustness to the communication topology because this is just the 14 bus system. There were two different topologies there. One of them is shown in solid lines here. One of them is shown in dashed lines. And as they're both connected. They both have to converge to the same thing, and in fact they do. Okay, well, I'm about out of time, and I'm also about out of slides, so let me just wrap this up. Just point out that we can also, I talked about the DC problem where we have linear measurements. We can also look at nonlinear state estimation, which is a model for the AC grid, and that actually is treated in the same paper that I just mentioned. Also, another problem, which is more like a communications problem, has to do with stabilizing the physical grid based on the cyber layer. And so if you want to use sensor measurements to stabilize the grid, you have to distribute those, that is, route those to the actuators or to whatever controls you have in the grid. But the sensors don't necessarily know what controls need the data that they're sensing. So they have to sort of multicast that out to hope that it gets to the right control elements. So you can look at this problem as a very similar kind of situation where you want to stabilize one system based on that has one topology based on routing in another system that has another topology, and this appeared last year and also in the Smart Grid JSAG series. And finally, I just want to mention another paper, which is by the way, this is Li-Feng Lai and Huxing Li. Li-Feng is another former postdoc of mine, and Huxing is a former graduate student of mine. I just want to mention this paper because it has all three elements. The games here in this paper, we look at this problem of competitive privacy in distributed state estimation, but in using multi-period games. That is, over time, using incentives to get in a multi-period game to get to induce cooperation among competitors in doing state estimation in a distributed fashion. And this is Veronica Belmega, and this is Lalitha again. Veronica is another former postdoc who's now in France. This appeared at NetGCoop in Avignon last year, and it's been submitted to Transactions on Smart Grid. Okay, so this is my last slide. So what have I talked about today? So I tried to give you an idea of some techniques from wireless networking and other fields like that, and how they might be applied in Smart Grid. I talked about this game theoretic idea of using game theory to model the interactions among nodes in the grid. Here we talked about how to use information theoretic ideas to look at the trade-off between privacy and utility and some information gathering problems in the grid. And then at the end I talked briefly about this problem of distributed state estimation. Okay, with that I'm done, and I'm happy to take questions. Thank you.
Okay, so we have time for a few questions.
You talk both about power line communication and also using a separate communication grid for controlling it. So do you have a gut feeling for if you will use power line communication solely for the control of the smart grid in the future? So is there a good case for?
Yeah, I mean, my guess is it would only be used for just short hop. Okay, I don't. I mean, that we looked at it for sort of all the way backhauling, but I think in reality it'd probably be used just for short hop. Even then, you might use wireless, but I think at best it would be good for short hop. That's my gut feeling for that. So, yeah. I mean, power line is used a lot for local area networking, which is very good. Once you get into long lines and things like that, it's much more difficult to deal with. So, other questions?
So you mentioned the query problem that you probe the database and then you can leak information. I was wondering, in the distributed setting, what's the adversary model? Who is the one who gets information? You mentioned the trade-off in privacy and utility in a distributed estimation setting. So what's who's a bad guy there?
Well, the bad guy is the other. I mean, in some way they're not bad guys in the sense that the user, the person that you're revealing data to, is one of your competitors in the marketplace. Okay, so in that respect, that's a bad guy. Okay, but you do want to share information with the bad guy because you want the bad guy to share information with you. So that's where the competition comes in. So there's another layer of you have privacy. You could think about a single problem where that bad guy doesn't have his own data to share, and you're just doing the first problem I talked about. But here it's sort of a two-way street basically. So is that okay? Thank you. It's a good question. Others?
Regarding these systems for estimating a distributed estimation, can you say a bit how robust they are? So saying, for example, there is one of the guys that doesn't really provide information he promised to provide. It's just some distorted version. Is this catastrophic or?
That's a good question. I really don't know. That's an interesting question. In other words, here that last bit is sort of based on a situation where you assume trust. So everybody is sharing legitimate information. Of course, if you start adding the competitive element in, then you can't necessarily assume that. There's a lot of work, I didn't talk about it here, but there's a lot of work in the smart grid having to do with problems like that, so-called bad data detection, right? How do you know that the data you're getting is legitimate when you're doing state estimation? And that's a whole field of, a whole subfield of this, and there's a lot of work in that area. A lot of that is very algebraic. You want to show, I have so many trusted meters or sensors. How many do I need, and where should I put them to be sure that I can overcome an attack of a certain sparsity or something like that? So there is a lot of work along those lines. I didn't talk about it here, but it's certainly a big concern, actually. The thing you brought up. So, okay.
You're allowed to ask questions even if you don't sit here.
Yeah.
So, any other questions from over here? Yeah. You're not excluded.
So my question is about more like the practice. So how far are we, let's say in the North America, if you're familiar with what's going on in the practice, let's say for energy trading, if these kind of algorithms are really being used, or are these many years ahead?
There are actually, you can buy software. Well, I don't know about these algorithms, okay, but I mean just the general idea of consumer-based energy trading decision making. That's in practice. There are startup companies in New York that's what they're doing. They're selling software to people with smart meters to do management like this. So yeah, I mean it's already, some of it is already there. At the institutional level, I mean, you may have seen a big announcement recently in the North American power grid they've just put in like a control center in upstate New York where all these PMUs are being reported in, and they're trying to use that to get advance warning of surges, and cascading failures. So the system they have now, they weren't able. The system they had previously, they weren't able to detect cascading failures. A cascading failure is a failure, a relay shuts off, all the power shunts around it, that overloads those relays, all those shut off, and pretty soon the whole northeast of the United States is blacked out. I mean, that happens. So with these so-called SCADA systems, they were not able to detect the wave front as it was coming in. Now with PMUs deployed, they can detect that and shut down. They can cut off regions and island regions so that things. So that's already been implemented too. So a lot of this stuff is becoming reality. But the thing is, it's a big data problem. There's a lot of data, and it's being used for certain things, but it could probably be used for a lot more. So. Oh. Yeah, this is. Anybody else wants to ask a question, you should move over here.
Yeah. Okay, so I have a very basic question. So I was thinking about the driving forces behind smart grids.
Mm-hmm.
So one of the driving forces could possibly be to more efficiently use the energy in the grid. Do you have any idea about the potential for energy savings, or are there other driving factors that are more important, like economy?
Well, okay. I don't. The answer is I don't know. There are projections, but I don't have them on the top of my head. But I think there are other driving forces, and it depends a lot on national goals. So in China, smart grid is more about reliability of the grid than it is about, say, giving consumer choice. Okay, because in some ways China is still electrifying. I mean, they're still putting electricity in a lot of places where they didn't have electricity before. There's it's billions of consumers, 1.4 or whatever. So reliability is the paramount thing. And so their smart grid is mostly about reliability. In the US, it's more about renewables, integrating renewables, preventing, which is also a reliability issue, preventing cascading failures, things like that. Responding to natural disasters and so forth. But so each, I don't know, in Europe I think maybe there's other motivations for using smart grid. But a lot of it has to do with national interests. So it all fits in the same umbrella, but not every country is interested in the same thing. So. I mean, in the U.S., I should say, national security is another issue, right? Counterterrorism. So, that's a lot of the bad data detection work has to do with trying to be sure, it's sort of assurance of the grid being able to operate in the event of a terrorist attack, for example, something like that. So, I mean, so there are different kind of things like that.